Hello, I'm going to continue lecturing about Force Vector Chapter 2, book by Hibbeler. And this section 2.5 is about um, three-dimensional vectors using Cartesian coordinates. So we're going to make use of XYZ frames that are right-handed. Essentially, if you rotate X towards Y, a right-hand screw will move in the positive direction of Z, or using the right hand, so you align your uh, fingers with the the x-axis, and the thumb will be the right hand. The thumb will be in the z-axis. Okay, so a vector A will have x, ax, ay, and az as components over x and y. So there's the vector you project it on the xy plane, a prime, and then you project a prime over x and y to get the ax and ay component. For az, you project the vector directly on the z-axis. That's the way of doing it. Now we can use unit vectors I, j, and k to express the original vector, and everybody knows I, j, and k are the unit vectors associated with the respective axis. And we can write again the components, the scalar components over x, y, and z of the original A vector multiplying with these unit vectors. All right. If we are interested in the magnitude given the projections over x, y, and z axis of a 3D reference frame, you get it applying this essentially Pythagorean theorem type law. We can use, there are other ways of expressing the orientation of vectors in 3 dimensions. That's by using what are called coordinate direction angles, the direction cosines. So you're looking at this figure. We have 3 angles that the vector A makes with the x, y, and z axis, and the cosines of these angles can be obtained with equations 2, 5. So you divide the projection over x-axis of vector A with the magnitude of A, see equation 2.4, to get cosine alpha. For angle beta form with the y-axis, you define the projection of the y-axis by the magnitude A, and to get the cosine angle form with the z-axis between the vector and the z-axis, you define the projection over z with the magnitude. Okay, so again, these are the direction cosines. And without using explicitly the cosine alpha, cosine beta, cosine gamma, we can write the unit vector now. So a unit vector associated with the given vector can be expressed in this form, and it has the property that cosine square of alpha, cosine square of beta, cosine square of gamma is 1, and allows us to determine the third of the cosine angle if we know already 2 of them. Okay. All right. So some forms of expressing vectors in Cartesian coordinates: the magnitude multiplied by the unit vector associated with the direction of the vector, using the direction cosines, or using the projection ax, x, ay, and az. There's another way in which you can express the orientation of a vector in 3D-dimensional space using x, y, z coordinates. That is by using the transverse angle and the azimuth angle, theta and phi respectively. So the z component of a vector AZ projection, that is, of the z-axis, you get it with this equation, magnitude of A times cosine of phi, and then the A prime projection, we saw something earlier, is going to be magnitude of A sine of phi, and you project this over x and y, and you ultimately get the formula for the vector A in 3 dimensions, or when we use the phi and that is the transverse and azimuth angle, phi and theta. If we do operations in 3 dimensions with Cartesian vectors, we just add them, their projections. So if I add A plus B, the resultant will have over x-axis magnitude AX plus BX, over y-axis AY plus BY, with their signs. Some can be negative. And for the z-axis, AZ plus BZ. Okay, or in general, if we add several or multiple 3D vectors, we can sum their x, their y, and their z components, and we multiply them with unit vectors I, j, and k. All right, let's move forward, and we're going to talk about position vectors. So this is a way in which we can locate a point in space, for example. So we have, like in this case, we have x, y, and z reference frame, and we have this point A. So to locate point A, we can report the x, y, and z coordinates of the point. So, and then there's another point B. So for A, what would be the x coordinate? We need to know we have the distance 4 here from this figure, so we have 4. That's AX. Over Y, we have 2 positive, so 2 is the Y projection, and Z is going to be negative 6. So in this case, A has coordinates 2, 4, and negative 6. Okay, so the position vector is defined by its and its position about the origin. It's defined by its x, y, and z components, and we use unit vector I, j, and k in a writing like this one. Okay, so yeah, this is position about the origin. We can see, however, earlier we had 2 points, so we can see the need, or can find a need to position 1 point, say B, with respect to A, and that will be R. That R is the position vector of B with respect to A in this case. So how do we get it? We use triangle rule, so we can write RA plus R equals RB. This is the equation here, and of course we can then explicit R, and if we know the x, y, and z projections of the individual vectors RA and RB, we can get the components of the vector that goes between A and B. Sometimes we use the index RAB to be specific that the vector is oriented from A to B, tail and head at B. So yeah, a vector RAB would mean that the tail is at A and the head is at B. Okay, so this would be the a position vector other than from the origin in 3 dimensions. All right, so there are some exercises. Next is section 2.8, force vectors directing along a line. A line is defined by 2 points. So we can have point A and point B in a force of some magnitude that it's acting between A and B. So 2 pieces of information. what is the direction of the force and what's the magnitude. So for the direction of the force, then it goes between A and B. We can find a unit vector, corresponding unit vector that goes or associated with direction AB. And we have the vector AB, also labeled as R. And if we divide it by the magnitude, then we get the unit vector associated with the direction from A to B. So we state the vector AB as xb minus xa, head minus tail, head minus tail, head minus tail over x, y, and z axis, and the unit vectors, and then we divide with the magnitude of the segment or the vector AB, which is the denominator. And we have this way, multiplied by the magnitude again. That's a separate piece of information that's given. Nothing to do with, in general, with the distance AB. And we get the force vector when the line of action is given in 3 dimensions. Next section is on what's called dot product. So dot products, you'll see them in use when calculating work of a force, for example. So it's an operation with 2 vectors that yields as a result a scalar. So vector A dotted with B, or A dot B, it'll have just magnet. Again, it's a scalar. So the magnet is going to be A multiplied, that is magnet of A multiplied by magnet of B multiplied by the cosine of the angle between the 2 vectors. Angle theta, it goes between 0 and 180. The dot product is commutative, so you multiply A and B, or A dot B is the same as B dot A. Scalar multiplication of a dot product, you magnify only one of the vector components or of the dot product, and it's also distributive. So A times B plus D is A times A dotted D plus A dotted D. In Cartesian vector formulation, so if we have A and B vectors given as projection AX, AY, and as Z, and B as BX, BY, BZ, then we can just multiply them in order. So AX was BX, well, this is the final answer, and then AY was BY, and then AC was BZ, and then we sum them. Or if we go like in algebra, so we take this and multiply 1, 2, 3, and take this and multiply 1, 2, 3, and take this and multiply 1, 2, 3. There will be so the unit vector dot products are all 0, but those that are in alignment. So that's why it's only this one left, and this one left, and this one left at the end. The rest would be 0. Anyway, so yeah, this is about the dot product, and we can use, in addition to what I was telling you later on, learning about work, or that's dynamics. Yeah, it's in dynamics. So we can evaluate the angle between 2 directions in space, or 2 direction in general. It could be in 2-dimensional space. So we multiply, or rather evaluate the dot product A B divided by the magnitude, and we get the cosine of the angle. So here really you apply the arc cosine, and you get the angle between 2 vectors A and B. And then it can also be used to evaluate the projection, a component along the direction of interest. So if we know a vector and we have a direction described by this unit vector, we can calculate the angle between the two directions by evaluating the dot product. Okay, and so yeah, it all becomes useful in as you will see, applications. So yeah, there are a few, and we'll be doing our share of them. So there's a review of this chapter. Don't neglect page 81 with a chapter review and everything that we studied like right now in this lecture. And this being said, I'm going to stop the recording.